how the smallest particles create the largest structures is often understood in a very simplified way. Many people imagine the universe as being divided into separate layers, where the very small belongs to physics textbooks and microscopes, and the very large belongs to astronomy, galaxies, and distant space. In this view, particles seem remote from everyday experience, and even more distant from the vast structures we see in the night sky. It can feel intuitive to think that tiny components matter only at tiny scales, while large structures emerge from entirely different principles. This assumption is not unreasonable, and it has shaped how the topic is often discussed, both in classrooms and in popular explanations. Yet when scientists look closely, they find that this separation between small and large is far less clear than it appears. What becomes evident over time is that the science is quieter and more gradual than the simplified picture suggests. The same basic components and interactions persist as scale increases, changing their influence slowly rather than abruptly. In this video, we will explore that continuity layer by layer, moving patiently from the smallest elements of matter toward the largest structures they help form. There's no need to hurry, and no need to hold on to conclusions. Each idea will be allowed to stand on its own, connected gently to the next. Welcome to AstraFlow. Here, science drifts quietly, and understanding comes without effort. If you find this space helpful, you're welcome to leave a comment or subscribe softly in your own time. Now, let's begin. To start, it helps to settle into what scientists mean when they speak about the smallest particles. In physics, particle does not always mean a tiny solid object, like a grain of sand scaled down many times. Instead, it refers to entities that carry measurable properties such as mass, charge, and energy. Some particles, like electrons, are associated with electric charge. Others, like quarks, combine to form more familiar matter. These components are not visible in any direct sense, but their presence is known through consistent experimental observation. Their behavior is described through mathematical relationships that have been tested repeatedly across decades in laboratories around the world. At this smallest scale, motion and interaction dominate the picture. Particles do not remain still. They interact constantly through forces that operate regardless of size. Even when isolated, particles carry energy, and that energy allows them to influence their surroundings. This is one of the first quiet clues that scale may not be as separating as it seems. The same interaction that shifts a particle's path can, when repeated countless times, contribute to the shaping of much larger systems. Nothing special has to happen for this to occur. No threshold is crossed. The accumulation itself is enough. Among the most important aspects of particles is that they follow rules with remarkable consistency. An electron behaves the same way today as it did billions of years ago. As far as current measurements can tell, this reliability is what allows structures to form at all. If particles behave differently from moment to moment, patterns could not persist. Instead, particles interact through stable forces such as electromagnetism and gravity, which remain present at every scale. At the smallest levels, gravity is extremely weak compared to other forces, but it does not disappear. It waits, quietly, until enough mass accumulates for its influence to become noticeable. Another key idea is that particles do not need to know what they are building. There is no guiding awareness or destination involved. Interactions occur locally between nearby components, following simple constraints. Yet when these interactions repeat across vast numbers of particles, patterns emerge that are not visible at the individual level. This is not unique to physics. It is a general feature of systems built from many interacting parts. The large-scale result carries no contradiction to the simplicity of the small-scale rules. It is simply their extended expression. When scientists examine matter at slightly larger scales, they find atoms. Atoms are stable arrangements of particles held together by electromagnetic forces. Each atom has a predictable structure, with electrons occupying regions around a nucleus composed of protons and neutrons. The distances involved are still extremely small, but the stability of atoms allows them to persist, combine, and repeat. This repetition is essential. Without it, matter would remain disordered and fleeting. With it, complexity becomes possible through gradual accumulation. Atoms, once formed, can join into molecules. Molecules are not fundamentally new substances in the sense of new rules. They are new arrangements of the same components. The forces binding them are the same forces that acted at smaller scales, now expressed across slightly larger distances. This step-by-step increase in scale does not involve sudden transformation. Each layer grows naturally from the one before it. This is one of the central ideas that will continue to appear throughout the video. Scale changes slowly, and the rules follow along without interruption. At this point, it may already feel easier to see how large structures could arise from small ones, not through dramatic leaps, but through patient continuity. Still, it is important to resist the urge to project the final outcome too quickly. The story does not rush from particles to galaxies in a single sweep. Instead, it pauses at each level, allowing matter to settle into forms that are stable under the conditions present. Temperature, energy, and time all play essential roles in determining which structures persist and which dissolve. Time, in particular, is often underestimated. When interactions repeat over long durations, even very weak influences can shape outcomes. A force that seems negligible in the moment can become decisive when applied steadily over millions or billions of years. This is one reason why gravity, though faint at the scale of individual particles, becomes the defining force at astronomical scales. It does not overpower other forces instantly. It accumulates its influence patiently. As we move forward in this exploration, the emphasis will remain on observation rather than interpretation. We will look at how scientists understand these processes through measurement, modelling, and careful comparison with what is seen in nature. There is no need to frame these ideas as surprising or profound. They are simply descriptions of how matter behaves when allowed to follow consistent rules over long periods and across expanding scales. For now, it is enough to rest with the idea that the smallest particles are not isolated from the larger structures. They are connected through continuity, repetition, and time. The universe does not switch mechanisms as it grows larger. It extends the same ones quietly until their effects become visible in forms we can recognize. When we stay at the smallest end of scale, the word matter begins to lose its everyday familiarity. At this level, matter is not something solid or still. It is defined by properties that can be measured, compared, and predicted rather than touched or seen. Scientists describe particles by how much mass they carry, how they respond to forces, and how they exchange energy. These properties are not decorative details, they are the entire story. Everything that follows, at every larger scale, depends on how reliably these properties behave. Among the simplest and most influential properties is mass. Mass determines how a particle responds to forces and how strongly it contributes to gravity. Even though the gravitational influence of a single particle is extraordinarily small, mass is never zero for particles that make up ordinary matter. This means that every particle, without exception, participates in gravitational interaction. The effect is imperceptible at first, but it is always present. Alongside mass, electric charge plays a crucial role. Charged particles attract or repel one another, shaping how matter arranges itself locally. These interactions occur constantly, whether or not they lead to lasting structures. Another defining feature of particles is that they follow statistical patterns rather than fixed paths. Instead of behaving like miniature planets, particles are better described by probabilities. This does not mean they are random in a careless sense. It means that their behavior is constrained within well-defined limits. Over time, these constraints produce predictable averages. When enormous numbers of particles are involved, those averages become remarkably stable. This is one of the quiet mechanisms by which order emerges. Predictability does not require certainty at every moment. It arises from consistency across many interactions. Energy is inseparable from this picture. Particles carry energy by virtue of their motion and their position within force fields. Energy determines whether particles remain bound together or drift apart. When energy is high, particles move rapidly and resist forming stable arrangements. When energy is lower, binding becomes more likely. This balance between motion and attraction is not decided once and for all. It adjusts continuously as conditions change. Temperature, pressure, and surrounding radiation all influence how energy is distributed among particles. At very small scales, electromagnetic interaction dominates how particles organize. Opposite charges attract like charges repel, and these tendencies govern the formation of stable configurations. The remarkable aspect is not that these interactions exist, but that they are so uniform. An electron behaves the same way no matter where it is found. Whether inside a laboratory instrument or drifting through interstellar space, its properties remain unchanged. This uniformity is one of the foundations of large-scale structure. Without it, matter could not assemble reliably. One grounded way to observe this stability is through atomic spectra. When atoms absorb or emit energy, they do so at specific frequencies. These frequencies act like signatures, revealing the internal structure of atoms. Astronomers detect the same signatures in light that has travelled for billions of years. This tells us that atomic behaviour has remained consistent across vast distances and times. The smallest structures do not evolve independently of the universe around them. They persist as reliable building blocks. It is also important to notice what particles do not do. They do not anticipate future configurations. They do not adjust behaviour to achieve larger outcomes. Interactions remain local and immediate. Each particle responds only to nearby forces and current conditions. Yet when this limited behaviour is repeated across immense numbers, the results extend far beyond the local scale. This is one of the reasons large structures can feel surprising. They are not planned, they are accumulated. As we remain with this scale, it becomes clear that complexity does not require complicated rules. The rules governing particles are relatively simple and few in number. What creates richness is repetition combined with time. When interactions are allowed to proceed uninterrupted, structures appear that would never be predicted by examining a single particle in isolation. The smallest scale does not explain the largest by itself, but it provides the stable groundwork upon which everything else depends. For now, it is enough to let this layer settle. Matter at its simplest is not empty or inert. It is active, consistent, and quietly influential. The same properties that define particles at the smallest scale will continue to shape what emerges as we move outward, step by step, without changing their nature. As we remain close to the smallest scales, attention naturally turns from the particles themselves to the forces that act between them. These forces are not dramatic events. They do not announce themselves. They operate continuously, shaping motion and arrangement without pause. Every interaction between particles is guided by a small set of fundamental forces, each with a specific range and strength. At this level, it is not size that matters most, but proximity. Forces act locally, linking particles to their immediate surroundings. Among these forces, electromagnetism is the most noticeable in daily life, even though it works invisibly. It governs how charged particles attract or repel one another, and it is responsible for nearly all the structural integrity of ordinary matter. The solidity of a surface, the resistance you feel when touching an object, and the stability of materials all arise from electromagnetic interactions between particles. At small scales, This force dominates because it is much stronger than gravity. Its influence does not fade quickly, and it organizes particles into stable arrangements. Another force, the strong nuclear interaction, operates at even smaller distances. It binds particles together within atomic nuclei, holding protons and neutrons in close association despite the repulsive electric forces between protons. This force is extremely powerful, but its reach is limited. It does not extend beyond the nucleus, and so its role is focused and contained. Its presence ensures that atoms can exist at all. Without it, matter would never stabilize into lasting forms. The weak nuclear interaction plays a subtler role. It governs certain types of particle transformation and decay. Though less intuitive, it contributes to the long-term evolution of matter by allowing particles to change form under specific conditions. These changes occur slowly and predictably, influencing how matter behaves over long timescales rather than shaping immediate structure. In this way, even rare interactions contribute to continuity. Gravity, though familiar, remains almost unnoticed at the smaller scales. Its influence between individual particles is so faint that it's easily overshadowed by other forces. Yet gravity never switches off. It does not need permission to act. It simply accumulates its influence as mass gathers. At this scale, gravity waits. It participates quietly, laying groundwork that will only become visible much later when enough matter comes together. One grounded observation that reveals the quiet power of forces is the stability of atoms. Atoms persist because forces balance one another precisely. Attraction and repulsion coexist in steady tension, allowing structures to remain intact without collapsing or flying apart. This balance is not fragile. It holds under a wide range of conditions. Atoms survive extreme cold, intense heat, and vast spans of time. Their persistence is a direct consequence of force interaction settling into equilibrium. What is notable here is that forces do not create complexity through variation, but through consistency. The same electromagnetic rules apply everywhere. The same gravitational law holds whether matter is sparse or dense. This uniformity allows matter to respond in predictable ways as conditions change. When particles move closer, forces strengthen. When they separate, forces weaken. There is no sudden shift in behavior, only gradual adjustment. Because forces act continuously, they also allow matter to respond to its environment without delay. Changes in energy, temperature, or density are reflected immediately in how particles move and bind. This responsiveness makes gradual structure formation possible. Matter does not need to pause or reorganize fundamentally. It simply follows the forces already present, adjusting moment by moment. As we stay with this layer of understanding, it becomes easier to see how forces act as quiet guides rather than active builders. They do not assemble structures deliberately. They constrain what is possible. They define which arrangements are stable and which dissolve. Over time, matter naturally occupies the stable configurations available to it. Nothing extra is required. For now, it is enough to let this idea rest. Forces act constantly, evenly, and without preference. They do not belong to one scale or another. They operate everywhere, shaping outcomes patiently as matter responds. As we move outward in scale, these same forces will remain, unchanged in character, even as their effects become more visible. Moving just one step outward in scale brings us to atoms, which are among the first stable structures formed from smaller components. An atom is not a solid object, but a system held together by forces that have already been quietly at work. At its center is a nucleus containing protons and neutrons, while electrons occupy regions around it. The distances involved are still extremely small, yet the arrangement is consistent enough that atoms can persist for long periods without losing their identity. This persistence is essential because it allows matter to exist in recognizable forms. The formation of atoms depends on balance. Electromagnetic attraction draws electrons toward the positively charged nucleus, while the electron's motion prevents collapse. This interplay creates stable configurations that do not require constant adjustment. Once formed, atoms remain intact unless acted upon by sufficient energy. This stability is not accidental. It arises directly from the predictable behavior of particles and forces already described. Nothing new is introduced at this stage. The same components and interactions simply settle into durable arrangements. Atoms come in different types, distinguished by the number of protons in their nuclei. This single difference leads to a wide variety of chemical behaviors, yet the underlying structure remains the same across all elements. Electrons respond to electric charge in identical ways, regardless of the atom they belong to. This uniformity allows atoms to combine reliably, forming molecules and larger structures without confusion or inconsistency. One grounded observation that reveals atomic stability is the persistence of elements over cosmic time. When scientists analyze light from distant stars and galaxies, they detect the same atomic signatures seen on Earth. Hydrogen, helium, and heavier elements behave identically across vast distances. This tells us that atomic structure is not a local phenomenon, it is universal. The smallest stable structures are shared across the observable universe. Atoms also introduce the idea of scale-dependent influence. At the level of individual atoms, gravity remains negligible. Electromagnetic forces dominate completely, determining how atoms interact with one another. This does not mean gravity has vanished. It simply means that, relative to other forces, its effect is too small to shape atomic structure. This selective influence will reverse later as scale increases and mass accumulates. The presence of atoms allows matter to occupy space in more complex ways. Atoms have size, even if that size is mostly empty space. When many atoms gather, they create density and resistance. These properties are not present at the particle level alone. They emerge from the way atoms fill space and respond collectively to forces. This is another example of how new characteristics appear gradually without altering underlying rules. As atoms form, energy becomes stored in their structure. Binding energy holds components together, and this energy can be released or absorbed under specific conditions. This stored energy plays an important role later, influencing how matter behaves in larger systems. At this stage, it is enough to notice that atoms carry with them a record of their formation, encoded as stability. When we rest with atoms, the transition from particles begins to feel less abstract. Matter gains endurance, it gains repeatability. Atoms can be counted, combined, and rearranged, but they do not disappear easily. This durability allows larger structures to form slowly and reliably over time. For now, it is enough to recognize atoms as a quiet turning point. They are not the goal of the process, but they are essential bridges between the smallest components and the larger structures to come. With atoms in place, matter is ready to organize further, without changing its fundamental behavior. When atoms are present in large numbers, they do not remain isolated for long. Their outer regions allow them to interact, forming bonds with other atoms nearby. These bonds arise from the same electromagnetic forces already at work, now acting across slightly larger distances. When atoms bond, they form molecules. Molecules are not new kinds of matter, but new arrangements of atoms held together in stable patterns. This step marks the beginning of structure that can vary widely while still obeying the same underlying rules. Molecular formation depends on conditions such as temperature and energy. When energy is high, atoms move quickly, and bonds are less likely to persist. When energy is lower, atoms can settle into stable relationships. This settling does not require coordination. It occurs whenever conditions allow. Over time, certain molecular arrangements become common, simply because they are more stable than alternatives. Stability, not complexity, guides which patterns remain. One of the most important features of molecules is repetition. The same molecular structures can form again and again under similar conditions. Water molecules, for example, have the same shape and properties whether they form in a laboratory, a cloud, or a distant planetary system. This repeatability allows matter to develop consistent behaviours at larger scales. Liquids flow, solids resist deformation, and gases expand, all because molecules interact in predictable ways. A grounded observation that stabilizes this idea is the behavior of materials under ordinary conditions. A block of ice maintains its shape because its molecules occupy fixed positions relative to one another. Liquid water flows because its molecules remain close but are free to rearrange. Steam spreads because its molecules move independently. These large-scale properties emerge directly from molecular arrangement and motion. No additional forces are required. As molecules gather, they begin to form patterns that extend beyond individual bonds. Crystals, for example, arise when molecules or atoms arrange themselves in repeating geometric structures. These patterns can extend over large regions, creating visible forms from invisible components. The regularity of crystals reflects the consistency of molecular interactions. Each bond reinforces the next, allowing structure to propagate outward. Molecules also carry internal energy associated with their bonds and motion. This energy influences how they interact with their surroundings. When energy is added, bonds may stretch or break. When energy is removed, molecules may settle into tighter arrangements. This responsiveness allows matter to adapt continuously without losing its fundamental identity. Structure is maintained through balance, not rigidity. At this scale, the influence of gravity is still minimal. Molecular interactions are governed almost entirely by electromagnetic forces and energy exchange. Yet as more molecules accumulate, mass increases, and gravity's presence grows slowly. It remains in the background, not shaping immediate structure, but preparing to become relevant as scale continues to increase. When we pause here, molecules reveal how complexity can emerge without instruction. There is no blueprint guiding their assembly. Patterns arise because certain arrangements are energetically favourable. Over time, these arrangements dominate simply because they last. This quiet selection process operates everywhere, from microscopic environments to vast clouds of matter in space. For now, it is enough to let this layer settle. Molecules show how small components organize into patterns that carry recognizable properties. They bridge the gap between individual atoms and the materials and structures that fill the world around us, preparing the way for larger forms to emerge naturally. As molecules accumulate, something subtle but important begins to happen. The focus shifts from individual bonds to the effects of many bonds acting together. Structure no longer depends on one connection at a time, but on the collective presence of countless interactions layered on top of one another. This is where accumulation becomes a shaping force. Nothing new is added to the system. The same molecules, following the same rules, simply gather in greater numbers and remain together for longer periods. Accumulation changes scale without changing behaviour. When molecules cluster, they occupy space more densely. Their combined mass increases, their collective energy distribution shifts, and their interactions begin to influence regions larger than any single molecule could affect. At this point, properties such as rigidity, flexibility, and resilience begin to appear. These properties are not found within a molecule itself. They emerge only when many molecules are present and interacting simultaneously. One of the most consistent ways accumulation shapes structure is through layering. Molecules settle into positions that minimize energy, and additional layers form on top of those arrangements. Over time, this creates thickness and volume. Sedimentary rock offers a clear observation of this process. Tiny particles, deposited gradually, form layers that harden into solid structures over long periods. Each particle follows simple physical rules, yet the result is a large, stable form that persists for millions of years. As accumulation continues, matter begins to resist change. A small number of molecules can be rearranged easily. A large number requires more energy to alter. This resistance is not intentional. It arises from the sheer number of interactions that would need to be disrupted. The more components involved, the more stable the structure becomes. This is why large objects tend to maintain their shape, while small collections of particles shift readily. Energy still governs how accumulation proceeds. If energy remains high, accumulated matter may disperse or remain fluid. If energy decreases, matter settles and consolidates. This balance determines whether accumulation leads to soft structures, rigid forms, or something in between. The outcome depends on conditions, not on design. Matter responds locally, and structure follows naturally. At this scale, gravity begins to make a quiet entrance. Individually, molecules contribute almost nothing to gravitational attraction. Together, their combined mass starts to matter. The effect is still weak compared to electromagnetic forces, but it is no longer negligible. Gravity does not reorganize molecular bonds, but it influences how large collections of matter move and settle relative to one another. Accumulation also introduces time as an active participant. Structures formed slowly tend to be more stable than those formed quickly. Gradual processes allow matter to adjust and settle into lower energy configurations. Rapid accumulation often traps energy and leads to instability. This difference becomes increasingly important as structures grow larger and more complex. When we pause at this layer, accumulation reveals itself as a quiet architect. It does not invent new interactions. It amplifies existing ones by repeating them across space and time. Large structures begin here, not through sudden transformation, but through steady gathering. Each molecule contributes a small, consistent influence, and together they create forms that endure. For now, it is enough to let this idea rest. Accumulation shows how size itself becomes a factor, turning simple interactions into stable structures through nothing more than repetition and patience. As accumulation continues, a quiet shift takes place. Structure begins to appear not only through gathering, but through arrangement. Matter does not pile up randomly forever. Given enough time and stable conditions, patterns begin to form. These patterns are not imposed from outside. They arise because certain configurations allow matter to remain at lower energy, while others do not last. Order, in this sense, is not the opposite of motion. It is the result of motion settling into balance. At this scale, order does not mean perfection or symmetry in every direction. It means regularity where regularity is favoured. Molecules adjust their positions in response to nearby forces, and those adjustments ripple outward. When one arrangement reduces strain or energy, neighbouring molecules tend to adopt similar positions. Over time, this local coordination extends across larger regions. The result is structure that looks intentional, even though it is entirely spontaneous. A clear, grounded example of this process can be seen in the formation of crystals. When atoms or molecules cool slowly, they often settle into repeating geometric patterns. Each unit aligns with those around it, not because of instruction, but because that alignment is energetically stable. The crystal grows as new components attach to the existing pattern, reinforcing the structure rather than disrupting it. The large visible form carries the imprint of countless microscopic decisions, each made locally and without awareness. What matters here is that order emerges without central control. There is no guiding plan that oversees the entire structure. Instead, each part responds to immediate conditions, and the collective response produces coherence. This principle holds far beyond crystals. It applies wherever matter is free to adjust gradually under consistent forces. Order is not added to matter. It is allowed to appear when conditions permit. Energy continues to play a shaping role. If energy remains too high, motion dominates, and patterns dissolve as quickly as they form. If energy is too low, matter may become locked into configurations that are stable but inflexible. Between these extremes lies a range where adjustment is possible and order can develop progressively. This balance is not rare. It occurs naturally in many environments, from cooling minerals to slowly condensing gases. As structures become more ordered, their influence extends outward. Ordered matter interacts with its surroundings differently than disordered matter. It may reflect light in consistent ways, conduct energy along preferred paths, or resist deformation more effectively. These effects are not new forces. They are the large-scale expression of many small interactions acting together in a coordinated pattern. At this stage, it is important to notice that order does not eliminate variability. Even within ordered structures, imperfections exist. Small deviations, impurities, and irregularities remain. These variations do not undermine the structure. Often, they contribute to its resilience. Absolute uniformity is not required for stability. What matters is that the overall pattern persists. When we let this layer settle, order reveals itself as a natural outcome of matter, responding patiently to forces and energy constraints. It is neither rare nor fragile. It arises wherever accumulation is allowed to proceed slowly enough for adjustment to occur. From this point onward, structure will continue to grow in scale, carrying forward the quiet regularities established here. As ordered structures become established, another influence begins to guide how matter settles, energy itself not just as motion, but as a shaping constraint. Energy determines which arrangements persist and which gradually dissolve. Matter does not choose forms freely. It moves toward configurations that require less energy to maintain. This tendency is not a goal or a direction. It is simply how physical systems behave when allowed to adjust over time. At this scale, energy flows through structures continuously. Heat moves from warmer regions to cooler ones. Vibrations pass from one part of a material to another. These flows influence how tightly matter binds and how easily it shifts. When energy can be distributed evenly, structures tend to stabilize. When energy accumulates unevenly, stress develops and rearrangement becomes more likely. The shaping effect of energy is constant, even when changes are slow. A grounded observation of this process can be seen in how materials cool. When molten rock cools gradually, its internal components have time to settle into organized arrangements. When cooling happens too quickly, disorder is preserved, and the resulting material may be brittle or irregular. The difference is not in the material itself, but in how energy was allowed to leave the system. Energy flow shapes form without altering the fundamental components involved. Energy also influences how structures respond to their surroundings. Materials expand when energy increases and contract when energy decreases. These responses are predictable and reversible within certain limits. They allow structures to adapt without breaking apart. This adaptability is essential as scale increases. Larger structures experience more varied conditions and must accommodate change without losing coherence. As matter grows in size, the cumulative effect of energy flow becomes more visible. Large structures store energy in their shape, their motion, and their internal arrangement. This stored energy influences how they interact with other structures. It affects how they collide, merge, or separate. Yet at no point does energy act independently of matter. It is always carried by particles and expressed through their interactions. At this stage, gravity begins to feel less distant. As structures accumulate mass, the way energy and gravity interact becomes more noticeable. Gravity encourages matter to draw inward, while energy associated with motion and heat resists collapse. The balance between these influences determines whether a structure remains diffuse or becomes more compact. This balance will become increasingly important as we move toward larger scales. For now, it is enough to rest with the idea that energy quietly guides form. It does not create structure by itself, and it does not impose patterns arbitrarily. It shapes what is already present by favouring arrangements that can persist under ongoing conditions. Structure emerges not because energy disappears, but because it finds pathways to distribute itself more evenly. With molecules organised and energy guiding their arrangement, matter begins to show properties that are recognisable at human scales. At this point, the distinction between individual components and the material they form becomes less important than the collective behaviour. Solids, liquids, and gases are not defined by the identity of their molecules alone, but by how those molecules move and interact as a group. This marks a shift from microscopic structure to macroscopic behaviour without any change in underlying rules. In solids, molecules occupy positions that remain relatively fixed. They still vibrate, but they do not drift far from their neighbours. This restricted motion allows solids to maintain shape and resist deformation. The strength of this resistance depends on how tightly molecules are bound and how ordered their arrangement is. The solidity of a material is not a separate property added on top of molecular structure. It is the direct consequence of many bonds acting together. Liquids represent a different balance. Molecules remain close, but they are free to move past one another. This mobility allows liquids to flow while still occupying a definite volume. The transition between solid and liquid states occurs when energy changes enough to alter molecular motion. No new interactions appear. Existing bonds simply loosen or tighten in response to energy flow. This gradual adjustment reinforces the idea that structure responds continuously to conditions. Gases form when molecular motion dominates attraction. Molecules move freely, spreading out to fill available space. Even here, interactions still occur. Molecules collide, exchange energy, and influence one another's paths. The difference lies in frequency and duration of contact. In gases, bonds do not persist, but interactions never cease. Matter remains active, regardless of form. A grounded observation that stabilizes this layer is the behavior of everyday materials under changing temperature. Ice melts into water. Water evaporates into vapor, and vapor condenses back into liquid. These transitions are smooth and reversible within certain ranges. They demonstrate how large-scale properties emerge from molecular behavior without requiring new principles. The same molecules participate in every state. As materials become larger and more complex, their internal structure affects how they interact with forces like pressure and gravity. A dense solid responds differently to gravity than a diffuse gas, even if both are made from the same atoms. This difference arises from how mass is distributed and how internal bonds transmit force. Structure influences response. At this scale, gravity begins to have more noticeable effects. While it does not determine molecular bonds, it influences how materials stack, compress, and flow. The weight of overlying material can change internal arrangements, leading to increased density or altered structure. Gravity does not replace electromagnetic forces. It adds another layer of influence that becomes more relevant as mass increases. When we pause here, materials reveal how large-scale behavior emerges naturally from small-scale interactions. There is no boundary where one set of rules stops and another begins. Instead, familiar properties like hardness, fluidity, and pressure are continuous expressions of molecular motion and bonding. This continuity will carry forward as we move toward even larger structures. As matter continues to gather into larger collections, gravity becomes increasingly difficult to ignore. Unlike electromagnetic forces, which act strongly over short distances, gravity acts weakly but persistently across space. At small scales, its influence is easily overshadowed. At larger scales, its cumulative effect begins to shape motion and structure in noticeable ways. This is not because gravity changes its nature, but because mass has increased enough for its influence to matter. Gravity responds only to mass and distance. It does not depend on composition, charge, or internal arrangement. Every piece of matter contributes equally, and every piece responds in the same way. This simplicity is part of what allows gravity to guide large-scale structure. As matter accumulates, gravitational attraction draws material inward, encouraging clustering rather than dispersion. This tendency operates slowly, often over immense spans of time. A grounded observation of gravity's growing role can be seen in how loose materials behave on Earth. Fine particles settle downward, compacting under their own weight. Over time, this pressure alters internal structure, increasing density and stability. The process is gradual and continuous. No sudden change announces gravity's arrival. Its influence strengthens simply because more mass is present. As collections of matter grow, gravity begins to compete with internal motion. Thermal energy encourages particles to move apart, while gravity encourages them to come together. The balance between these influences determines whether a structure remains diffuse or becomes more compact. When motion dominates, matter spreads. When gravity gains the upper hand, matter contracts. This balance does not require fine-tuning. It adjusts naturally as conditions evolve. At this stage, gravity influences shape as well as motion. Large collections of matter tend toward rounded forms, because gravity pulls equally in all directions toward the center of mass. This tendency becomes visible in planets and stars, but its roots appear much earlier, whenever matter is free to rearrange under its own weight. Shape emerges as a response to force, not as an imposed design. Gravity also links separate regions of matter, allowing distant components to influence one another. While electromagnetic forces diminish rapidly with distance in structured materials, gravity continues to act across gaps. This long reach allows gravity to coordinate motion on scales far beyond those of molecules or materials. It is here that gravity begins to prepare matter for even larger assemblies. When we let this layer settle, gravity appears not as a dramatic force, but as a steady organizer. It does not disrupt existing structures at small scales. It waits until enough mass is gathered, then gently reshapes motion and distribution. From this point onward, gravity will increasingly guide how matter arranges itself, setting the stage for structures that extend far beyond familiar experience. When gravity becomes influential enough, matter begins to organize on scales far larger than any material structure on Earth. In space, where there are no solid surfaces to support weight, gravity acts without obstruction. Clouds of gas and dust drift slowly, shaped by the combined mass of countless particles spread across vast regions. At first, these clouds appear diffuse and quiet, with particles moving independently, guided only by gentle attraction and residual motion. Over time, small variations begin to matter. Regions that are slightly denser than their surroundings exert a slightly stronger gravitational pull. This difference is minimal, but it is enough. Nearby particles drift inward, increasing density further. The process reinforces itself, not through sudden collapse, but through gradual concentration. Nothing needs to happen quickly for gravity to be effective. It works best when it is allowed to act patiently. As matter gathers, internal motion responds. Particles falling inward gain speed, and that motion translates into heat. Energy builds as gravitational potential is converted into thermal energy. This heating resists further collapse, creating a temporary balance. Gravity pulls inward, while rising temperature pushes outward. The structure that forms is not static. It adjusts continuously, responding to small changes in mass distribution and energy flow. A grounded observation of this process can be seen in star-forming regions observed by telescopes. Vast clouds of hydrogen and dust show subtle clumping, with brighter, denser regions embedded within darker surroundings. These regions are not yet stars, they are concentrations where gravity has begun to dominate locally. the structure remains soft and incomplete, shaped more by balance than by final form. As contraction continues, matter becomes more organized. Collisions between particles increase, redistributing energy and smoothing motion. Over long periods, this leads to more coherent inward flow. Gravity does not pull everything in at once. It gathers matter layer by layer, allowing energy to radiate outward as the structure tightens. This gradual release of energy is essential. Without it, collapse would halt prematurely. Eventually, some regions reach conditions where pressure and temperature become high enough to support new internal processes. At this stage, a star may begin to form. Yet even here, the transition is not abrupt. The emerging star remains embedded in its surrounding material, exchanging energy and matter with it. The boundary between cloud and star is not sharply defined. It develops slowly as balance shifts. When we pause at this layer, the formation of stars illustrates how small-scale interactions extend upward through gravity. The same particles and forces are present, now acting collectively across immense distances. Structure emerges not from sudden events, but from long-standing balance between attraction and motion. Gravity, once negligible, becomes the quiet architect of luminous form. As stars take shape, they do not exist in isolation. They form within larger systems, guided by the same gravitational influences that brought them into being. Once a star has emerged, its mass immediately becomes part of a broader gravitational landscape. Nearby stars respond to its presence, just as it responds to theirs. Over time, these mutual influences lead to organized motion, not through coordination, but through shared attraction. Stars that form from the same cloud tend to remain loosely associated. Their initial motions are similar, and gravity prevents them from drifting apart too quickly. These groupings can persist for millions or billions of years, gradually evolving as stars exchange energy through close encounters. The result is not a rigid structure, but a dynamic one, where motion remains orderly without being fixed. As more stars gather, larger patterns appear. Gravity encourages stars to orbit common centers of mass, forming clusters and eventually galaxies. These systems are defined less by physical contact and more by shared motion. Vast distances separate individual stars, yet gravity links them into coherent structures. The scale has increased dramatically, but the mechanism has not changed. Attraction remains the guiding influence. A grounded observation of this process is found in the rotation of galaxies. Stars orbit their galactic centers in stable, repeating paths. These motions persist over immense timescales, indicating long-term balance rather than instability. The galaxy holds together not because stars are close, but because gravity extends across the entire system, binding motion into a unified pattern. Within galaxies, structure continues to refine itself. Spiral arms, central bulges, and extended halos emerge as stars respond collectively to gravitational distribution. These features are not solid objects. They are regions where motion aligns over time. Stars move in and out of them, yet the overall pattern remains. Structure here is statistical rather than fixed, maintained by the average behavior of countless components. Energy still plays a shaping role. Stars exchange energy through gravitational interactions, slowly altering their orbits. Some drift inward, others move outward. Over long periods, this redistribution leads to gradual change without disruption. The system remains recognizable even as its internal details evolve. When we rest at this layer, galaxies demonstrate how gravity organizes matter at its largest visible scales. The same accumulation that once shaped molecules now shapes star systems, extended across space and time. Nothing new has been added. The smallest particles remain present, participating quietly in structures that span thousands of light years. As galaxies persist and evolve, time becomes an increasingly visible factor in how structure develops. At smaller scales, change can feel immediate, But at galactic scales, time stretches into millions and billions of years. Processes that seem slow by human standards become the primary drivers of transformation. Gravity, motion, and energy exchange operate continuously, shaping structure not through speed, but through duration. Within galaxies, matter does not remain fixed in place. Stars age, release material, and eventually return part of their mass to their surroundings. This material mixes with existing gas and dust, subtly altering the composition of future generations of stars. The structure of the galaxy remains even as its contents cycle. Time allows the same particles to participate in many stages of organization, without ever leaving the system entirely. A grounded observation of time's role can be seen in the distribution of elements within galaxies. Heavier elements are more common in regions where many generations of stars have lived and ended. This pattern reflects long-term accumulation rather than sudden change. Each generation contributes a small amount, and over time, those contributions become significant. Structure carries a memory of its own history, written gradually rather than recorded at once. Time also smooths motion. Over long periods, irregular paths tend to average out. Stars exchange energy through gravitational encounters, leading to more stable distributions. Extreme motions become less common, not because they are forbidden, but because the system naturally settles into configurations that persist. Stability here is statistical, maintained by countless small adjustments rather than rigid constraints. At these scales, nothing is truly permanent, yet nothing disappears abruptly. Structures endure because change is distributed across time. The galaxy you observe at any moment is a snapshot within a continuous process. Its overall form remains recognizable even as its internal details shift. Time allows structure to exist without requiring stasis. When we pause with this layer, time reveals itself as an essential partner to scale. Small interactions need long durations to produce large effects. Gravity's quiet pull, energy's gradual redistribution, and matter's persistent presence all rely on time to express their influence fully. Without time, the connection between small particles and large structures would remain invisible. As scale and time extend together, certain patterns begin to appear again and again. These patterns are not exact copies, but familiar arrangements that arise under similar conditions. From the smallest clusters of particles to the largest systems of stars, matter tends to organize in comparable ways when guided by the same forces. This repetition is not coincidence. It reflects the limited number of stable solutions available to physical systems. One of the most consistent patterns is clustering. Particles cluster into atoms, atoms into molecules, molecules into materials, and stars into galaxies. At each level, attraction competes with motion, and balance produces structure. The details change, but the relationship does not. This continuity allows scientists to recognize the same principles operating across vastly different scales. A grounded observation of repeating patterns can be seen in rotation. Molecules rotate, planets rotate, and galaxies rotate. The source of rotation varies, but the outcome is similar. When matter gathers under attraction, any small imbalance in motion tends to be preserved. Over time, this leads to organized rotation rather than random motion. Rotation becomes a stable way for systems to distribute energy while remaining bound. Another recurring pattern is layering. From atomic shells to planetary atmospheres, matter often arranges itself in layers, each shaped by local conditions. Layers form because forces and energy distributions vary with distance. What matters is not the material itself, but the way influence changes across space. Layering allows structures to remain stable while accommodating variation. Patterns also appear in the way systems respond to disturbance. Small changes are often absorbed locally, while large changes spread gradually. This behavior is visible in materials, ecosystems, and galactic systems alike. Stability does not mean immobility, It means the ability to adjust without losing overall form. These repeating patterns do not imply design or intention. They emerge because physical systems are constrained by the same rules everywhere. When matter follows those rules over time, certain arrangements become common. Rarity does not indicate impossibility, and familiarity does not imply simplicity. Patterns persist because they work. When we let this layer settle, repetition across scales becomes a quiet reassurance. The universe does not reinvent itself at each size. It extends the same tendencies, allowing small structures to echo within large ones. This echo is not symbolic, it is mechanical, grounded in consistent interaction. As patterns repeat across scale, it becomes clear that human perception occupies only a narrow middle range. We are well adapted to notice objects that persist at our size and time scale, but much less sensitive to influences that are either far smaller or far slower. This limitation shapes how structure is commonly understood. What is too small appears insignificant. What is too slow appears static. Yet both are continuously active, contributing to outcomes that only become visible when viewed from a broader perspective. At small scales, change happens constantly, but its effects are distributed. Individual particle interactions feel negligible because they do not announce themselves. At large scales, change happens so gradually that it can be mistaken for permanence. Mountains appear still, galaxies appear fixed, and even stars seem unchanging across a lifetime. In reality, each of these structures is in motion, adjusting subtly under forces that never pause. A grounded observation of this perceptual limit can be seen in erosion. A single grain of sand moved by water has no visible impact. Over centuries, the same process reshapes entire landscapes. The force involved does not increase. Time simply allows small actions to accumulate. This illustrates how scale and duration interact to produce effects that lie beyond immediate perception. Scientific tools extend perception beyond these limits. Instruments allow measurement of tiny changes and slow motions, revealing continuity where intuition suggests separation. Through careful observation, scientists trace how small-scale interactions persist upward, linking domains that once seemed unrelated. The universe does not hide its structure. It unfolds it patiently, requiring attention rather than speed. When we rest here, the role of perception becomes clearer. Large structures are not created by large actions alone. They are built from small, steady influences that lie outside ordinary awareness. Understanding emerges not by forcing perspective, but by widening it gently, allowing different scales to coexist without competition. As understanding widens beyond natural perception, tools become essential companions. Instruments do not replace human senses so much as extend them, allowing observation to reach into scales that would otherwise remain abstract. Microscopes reveal the arrangement of atoms. Detectors capture particles passing silently through matter. Telescopes gather light that has travelled across immense distances and times. Each tool is designed not to add interpretation, but to record interaction as faithfully as possible. At small scales, tools reveal consistency. Measurements made in different places and at different times align closely, showing that particles behave the same way regardless of context. This reliability is what allows scientists to link the smallest interactions to the largest outcomes. Without it, structure would appear fragmented, with each scale operating under separate rules. Instead, instruments reveal continuity, one layer at a time. At larger scales, tools reveal patience. Galaxies rotate too slowly to be noticed directly, but repeated observation shows their motion clearly. Gravitational effects that seem static are revealed as ongoing processes when viewed across longer intervals. These observations do not change the structures themselves, they change how those structures are understood. What once seemed fixed becomes active. and what once seemed isolated becomes connected. A grounded example of this extended perception is the mapping of cosmic background radiation. Subtle variations in temperature, almost imperceptible, reveal how matter was distributed in the early universe. From these small differences, scientists infer the seeds of later structure. The observation does not explain everything at once. It offers a calm trace, showing how small irregularities can grow into large patterns over time. Tools also remind us of limits. Every instrument has resolution, and every measurement carries uncertainty. These limits do not undermine understanding. They define its boundaries. By acknowledging what cannot yet be resolved, science avoids forcing conclusions where continuity is still unfolding. Structure is traced patiently, not completed prematurely. When we pause here, tools appear not as sources of authority, but as quiet extensions of attention. They allow the same principles to be followed across scales that human senses alone could not connect. Through them, the smallest particles and the largest structures remain part of the same observable story. As observations accumulate across scales and over time, another pattern becomes clear. Structure is not static, even when it appears stable. Everything that forms continues to change, guided by the same rules that brought it into being. Evolution in this context does not imply progress or direction. It simply describes ongoing adjustment as conditions shift and matter responds. At small scales, evolution may take the form of gradual rearrangement. Bonds form and break, materials slowly alter their internal structure, and energy redistributes until balance is restored. At larger scales, evolution becomes easier to see. Stars age, systems reorganize, and galaxies slowly change shape as matter moves within them. The pace differs, but the process remains continuous. A grounded observation of structural evolution can be seen in planetary systems. Orbits that are stable over long periods may still shift subtly as bodies exchange energy. These changes do not announce themselves dramatically. They accumulate over time, leading to arrangements that differ from their earlier state while remaining recognizable. Structure persists through adaptation, not through rigidity. Evolution also involves loss as well as formation. Matter disperses as readily as it gathers when conditions allow. Stars release material, systems eject components, and structures gradually thin at their edges. This dispersal is not a failure of organization. It is part of the same balance that allows structure to form in the first place. Attraction and motion remain in constant negotiation. Time ensures that no configuration is final, yet time also ensures that change is rarely abrupt. Systems tend to move through a sequence of nearby states rather than jumping between extremes. This continuity allows large structures to endure even as their details shift. Stability is not the absence of change. It is change distributed smoothly. When we rest with this layer, evolution appears as a quiet extension of structure rather than its opposite. The smallest particles continue to participate, rearranged and reused, shaping forms that adjust without breaking apart. Structure, once formed, does not end. It continues, adapting as part of the same ongoing flow. As structure evolves across time and scale, it becomes natural to notice where human experience fits within this continuity. Our bodies, our environment, and the materials around us are composed of the same particles and governed by the same forces already described. There is no separate category for human-scale matter. The difference lies only in scale and organization, not in substance or rule. At this middle scale, structures feel solid and persistent. Objects appear stable because the interactions that maintain them operate far faster and far slower than our immediate perception. Molecular bonds adjust quickly enough to absorb small disturbances, while gravitational and structural changes occur slowly enough to seem fixed. This balance creates the sense of permanence that defines everyday experience. A grounded observation of this position can be found in the built environment. Buildings remain standing because countless molecular bonds and material structures distribute forces evenly. Yet those same buildings respond to gravity, temperature, and time in ways that mirror larger systems. They settle, expand, contract, and slowly wear down. The processes are familiar because they operate within a scale we can observe directly. What is notable is that nothing special happens at the human scale. There is no boundary where new principles appear. The same accumulation, ordering, and energy flow continue uninterrupted. Human-scale structures are temporary expressions of deeper continuity, shaped by the same influences that govern stars and galaxies, simply compressed into a narrower range of size and time. Recognizing this position does not require reflection beyond observation. It is enough to see that human experience sits within a larger spectrum of structure. We neither interrupt nor complete the process. We participate in it, briefly and locally, as matter organized under consistent rules. When we let this layer settle, scale feels less hierarchical and more continuous. The smallest particles, the largest structures, and everything in between remain connected through the same quiet interactions, unfolding without emphasis or distinction. As the view widens once more, attention returns to the idea of continuity itself. Small and large are often spoken of as opposites, yet in practice they are adjacent moments along a single process. There is no point where matter stops being small and suddenly becomes large. There is only steady extension. Particles participate in atoms, atoms in materials, materials in bodies, bodies in systems, and systems in galaxies. Each level remains present within the next, not replaced, not erased. What holds this continuity together is not complexity, but persistence. The same interactions repeat, slightly reshaped by scale and circumstance. Forces do not retire as structures grow. They remain active, joined by others whose influence becomes noticeable only when mass and distance increase. The result is a layered system where no level is independent. Each depends on the stability of the one beneath it and contributes to the behavior of the one above. A grounded way to observe this continuity is through motion. A small vibration in a material travels outward, becoming a wave that affects a larger region. A local gravitational imbalance spreads its influence across a system. Cause and effect do not stay confined. They propagate, linking regions that appear separate when viewed in isolation. Structure is not segmented, it is shared. This shared structure means that understanding does not require jumping between explanations. The same principles apply, adjusted gently for context. What changes is not the rule, but the scale over which it operates. When this is allowed to remain clear, complexity becomes less intimidating. Large structures no longer feel disconnected from their origins. They feel like natural extensions. When we pause here, the distinction between smallest and largest softens. The universe appears less like a collection of separate layers and more like a continuous field of interaction, where every scale participates in shaping every other. Nothing stands alone. Nothing needs to. As the exploration settles, there is no need to gather ideas into a conclusion. The continuity described does not resolve into a final statement. It continues on its own. The smallest particles remain in motion, interacting as they always have. Larger structures persist, adjusting slowly, shaped by the same quiet influences. Nothing arrives at completion, and nothing needs to. The process itself is stable. At this point, attention can soften. The distinctions between scale, between particle and structure, no longer require active focus. They exist together, layered gently, each supporting the next without effort. The universe does not rush from one form to another. It allows change to unfold at its own pace, distributing motion across time and space evenly. There is rest in recognizing this steadiness. Forces continue to act. Energy continues to flow. Matter continues to arrange and rearrange. Yet none of this demands response or interpretation. It happens whether it is noticed or not. Understanding does not need to hold on. It can drift, knowing that continuity remains, everything flows. Sleep in that motion.